Hello everyone, and welcome to this front-to-back MMIC design flow with ADS. This presentation will highlight the design flow steps in ADS that will ensure a first-pass success with lowest cost and highest yield. MMIC designers are always challenged to reduce costs and get their device to market fast and ahead of the competition. ADS allows you to meet these challenges. It provides you with unique and advanced set of tools to create robust designs, first-pass success, and high yield. It provides you with a complete set and continuously updated process design kits from all major MMIC foundries. It gives you a complete set of advanced simulation tools seamlessly integrated in one single environment, all the way from schematic entry to production and packaging of your MMIC. It gives you the ability to verify prior to fabrication that the MMIC meets all specification in its final package using seamlessly integrated planar EM and 3D EM tools. And also it gives you the ability to provide true circuit verification to all wireless standards prior to and post fabrication by using a complete set of the most accurate wireless verification tools. So this is the complete front-to-back MMIC design flow solution in ADS, all done in one single environment. Its many features here, as we will discover shortly, bring a higher level of productivity to the MMIC design process. So after having obtained the design specs, we start by choosing the appropriate Foundry design kit with all the needed elements and models to start your design. It is then followed by the schematic entry, then followed after that by the statistical design phase using ADS unique tools that converts your initial design into a highly robust design with first-pass success and high yield. Next, an early-on verification to wireless standards specs as is shown in order to verify that your design meets its wireless specs prior of starting the physical design part. Now, all the right side here shown shows the physical design section, which includes the creation of the layout and using planar and 3D integrated EM tools to ensure design accuracy and first-pass success. DRC, LVS, and packaging the MMIC are all included in this physical verification cycle of the design flow. Part 1 of this presentation now will focus on the schematic entry of the design flow. So we start from the models and Foundry design kits, then we have our schematic entry design, then we use the DFM tool, the statistical analysis, to convert our design into a solid, robust design, and then we will verify it through wireless verification standards. And then we will move to part 2, which is the physical design aspect. So here's the slide on the Foundry, the MMIC foundries, and the MMIC foundry partners. See, strategic partnerships with the leading MMIC foundries shows Agilent's established leadership in the MMIC design. These relationships with all foundries ensure that more and more foundry processes support the complete MMIC design flow in ADS, including the physical design. Agilent EEsof has more MMIC PDKs than any other EDA vendor in the industry today. It provides you with the widest choice of foundries for MMIC design with the best availability and price performance. Agilent's PDKs are jointly created by Agilent and the foundry and are fully validated and always regularly maintained and updated. So designers always have access to the latest and most up-to-date foundry models that reflect the most recent processes. If the Foundry have a change in the process, they automatically update the design kit for you. So in summary, ADS has a complete set of MMIC process design kits, the only ones in the industry to be fully verified, fully supported and maintained and continuously updated by the foundries. Now this slide shows the Advanced Model Composer, AMC technology in ADS. Advanced Model Composer is a patented ADS technology that allows designers and foundries to create arbitrary parameterized passive structures and shapes with built-in EM effects. The result is compact models that can be used and for simulation, for fast tuning, for optimization. It is enabling the designer to converge on specified parameters in seconds. So AMC technology brings you the accuracy of EM simulation, but at the speed of analytical models into a single user-defined compact model. So it is shown here that you can create a palette, for example, for spiral inductor, and you can bring the spiral inductor in the schematic page and simulate it very fast, but the simulation is actually done using EM technology. Here's an example taken from the TriQuint 0.15 pHEMP MASC design kit. It shows a spiral that has a range of widths and lengths that have been generated using AMC. So you can see here in the window L and W inductor width. The range has been simulated between 45 and 95 micron. That means you can change those length and width between this range and the models will be valid, and it is EM simulated with EM accuracy. Here what we have is an example of a line from that kit that can be altered by adding a bridge to it in the center or offsetting the bridge to the right or to the left, and by changing its angle, the line angle, all from this dialog box. You can just input those parameters in the dialog box and automatically it will do that for you. The help menu of this line automatically show you a full set of the layers and line types with their current densities as shown on the right side here. So designers then have a choice on what type of line to use and how many layers. Each type contains different set of layers with different current densities. It's very useful in the design of power amplifiers. And the next slide shows all the elements from this design kit that are used in a simple LNA, one-stage LNA design. After having found a good design kit and models, now the next step is to start our design using the schematic entry along with the various advanced circuit simulators, such as ADS, nonlinear harmonic balance, circuit envelope simulator, transient and convolution simulators, linear and system simulators, and planar and 3D EM simulators, all integrated together in a single design environment. So let us show how this step is done in ADS. As I walk through this presentation, I will keep referring to this simple one-stage low-noise amplifier demo in order to illustrate the steps taken by designers to build a design. We start from a FET model taken from the design kit. So you can see the FET here. We want to characterize it. We want to understand how the characteristic of this FET and where to bias it for our low-noise amplifier design. In ADS, we have insert templates. There are many templates that you can insert automatically in the schematic page. In this case, I inserted the FET curve tracer.